Welcome to a new episode of FrameMinds Engineering. Today we're going to apply the concepts we learned about beam analysis and design. Let's start by introducing our problem. Here we have a flooring system with cross beams running from one girder to the other. The girders carry the loads from the cross beams to the columns. The cross beams have a span of 30 feet. This flooring system is located on the second floor of a retail store. The cross beams are connected to the girders using a single angle connection. The single angle connection is a connection that is assumed to not carry any bending moment. I've discussed the assumptions involved with different support conditions in a previous video. You can find it in the description down below. Let's have a look at the cross section. The cross beams are equally spaced with 7 feet in between them. The cross beams are carrying a 4-inch thick reinforced concrete slab with normal weight concrete. The area covered by the flooring system is planned to be partitioned by a maximum of 5 steel partitions. First, let's find out the maximum expected loads on our structure. For that, we have to refer to ASCE 7, where a table of minimum uniformly distributed and concentrated live loads to be considered for different applications are provided. Because we have a flooring system on the second floor of a retail store, the expected uniform and concentrated live loads are as follows. A similar table is available for the minimum design dead loads. The load caused by the concrete slab per unit thickness is given as 12 pounds per square foot. Weight of concrete with reinforcement can be calculated using the density of the concrete and the weight of the used steel reinforcing bars instead of using the table for a more accurate assessment of the load. The movable steel partitions have an approximate uniformly distributed load of 4 pounds per square foot each. And thus, we end up with 48 pounds per square foot for the concrete slab and 20 pounds per square foot for the partitioning. However, the partitioning will be considered as live load because it is movable and might change within the lifespan of the structure. Let's have a closer look how these loads are carried over to the cross beams. Each beam carries the loads from half of the area between it and its neighboring beam from either sides, and thus the total width of the area of the load carried by the beam is 7 feet, and it's called the tributary width. This means that the linear dead load on the beam is the area load of the slab multiplied by the tributary width, which gives 336 pounds per foot. Similarly, the total linear live load coming from both the partitioning and the expected uniform live load is 665 pounds per foot. The weight of the beam will be added to the dead load once the beam size has been chosen. Also, the concentrated live load location needs to be determined such that it will induce the maximum bending moment or the maximum shear in the beam. Let's discuss the engineering assumptions involved in our analysis. Because the cross beams are connected to the girders using a single angle connection, we can assume that the cross beams are simply supported beams. Because we are trying to meet the serviceability criteria for maximum deflection, which is the length of the beam divided by 360, we can conclude that we have small deformations. When having small deformations, the linear analysis is adequate to represent our beam. And because we have a linear analysis, we can use the principle of superposition. This means that when evaluating the response of a beam loaded by a uniform load and a concentrated load, this is equivalent to evaluating the responses of the concentrated load and uniform load cases separately and adding the results. Notice that we still need to determine the location of the concentrated load that will cause the highest bending moments and/or shear stresses in the beam. So let's have a look at that together. To study the effects of moving the point load on the simply supported beam and finding the load location with the maximum bending moment or the maximum shear. Let's try to move the point load in this example in this simply supported beam. We can see how the shear diagram changes and how the bending moment diagram changes, and we can also see how we achieve the maximum bending moment when the load is exactly at the center of the beam, and how we achieve maximum shear when the load is near the edges or the supports. After determining the loads, these loads have to be factored according to the relevant design codes. In this case, ASCE 7, where different load combinations are given for different load cases. In our case, we have dead and live loads, and thus the chosen load combinations is 1.2 dead plus 1.6 live. This gives us a total factored uniform load of 1467.2 pound per foot. In order to calculate the maximum bending moments, we can refer to the equations provided in the AISC construction manual, and after plugging the numbers in, we receive a moment of 165 foot-kips. The same is done for the concentrated load, in which it is factored and consequently used to determine the maximum bending moment of 12 foot-kips when the load is positioned in the middle of the beam. The uniform load tables are also used to calculate the maximum shear forces in the beam, but we know from the previous illustration that the maximum shear due to a single concentrated load is the value of the load itself when positioned close to either of the supports. And thus, a total bending moment of 177 foot-kips and a maximum shear of 23.6 kips is obtained. Now that we have the moments, we have to determine the different possible failure modes or limit states in which the crossbeam can fail due to flexure. After referring to the AISC 360 Chapter F, we can avoid local buckling failure modes by only choosing compact sections, which can only fail due to flexural yielding or lateral torsional buckling. I discussed the different failure modes of beams under flexure and shear in a previous video. Link to that video will be in the description down below. Because the top flange of the beam is continuously laterally supported by the reinforced concrete slab, the beam cannot fail due to lateral torsional buckling. This means the crossbeam can only fail due to flexural yielding. In the AISC construction manual, the W sections are sorted in Table 3-2 according to their flexural yielding strength. Based on that, we can choose the W section with the moment resistance above the factored moment of 177 foot-kips. This section is W8 by 48 with a bending resistance of 184 and the shear resistance of 102, which are both greater than the demanded values. And to check the deflection requirements, the moment of inertia about the strong axis Ix is needed as well. The other values in the table refer to the reduced bending strength due to lateral torsional buckling at unbraced length L sub r, and Bf is the slope of the linear segment between M sub p and M sub r to linearly interpolate the bending strength in case the unbraced length lies in between L sub p and L sub r. Now that the trial section has been chosen, its own weight has to be taken into account as a dead load. In American sections, the second number always refers to the nominal weight of the W section. By factoring the weight and using the previously used table, we can calculate the extra bending caused by the own weight of the beam. Even after adding the extra moment, the total moment is still less than the strength, so we move on to the shear strength. The same happens when adding the extra shear as well. To find the maximum deflection, we have to consider the unfactored uniform and concentrated live load separately and add the deflections together. This ended up being larger than the maximum allowed limit of L over 360, and thus a new section with a higher moment of inertia should be chosen. This is accomplished by equating the maximum allowed deflection of 1 inch to the sum of the deflections and taking moment of inertia I sub x as an unknown. After solving for I sub x, we refer to Table 3-3 in the AISC construction manual, which sorts W sections according to their moment of inertia. We choose the lightest weight with a moment of inertia above 452. This section is W18/35. Next, we go back to Table 3-2 to check whether the bending and shear strength both exceed the demand values. Now all the requirements are met, and W18/35 is our chosen section as a crossbeam for the flooring system. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.